Good morning, class. Good morning.
Morning.
Okay. Are you charged or you want me to charge you for the class? Okay. Are you ready for this class?
Yeah. Yeah.
Okay. Again, after me repeat 3 sentences. I'm blessed.
I'm blessed.
Not I am blessed. I'm blessed.
I'm blessed.
I'm happy.
I'm happy.
I'm good at math.
I'm good at math.
Okay. So today I'm going to talk about operational amplifier. How many of you have studied operational amplifier or op-amp? Not all of you. So from these guys, what are operational amplifiers? Again, how many of you have studied or you studied before? Op-amp. Nobody. Iron? What is an op-amp? Yes. That is clear from its name, operational amplifier. So it's doing mathematical operations for us. Why do we use operational amplifier in circuits? Because sometimes we need some mathematical operations. That's why we use it. This is nothing, just an IC. I was down in the lab to look for an IC to bring it for you, but I couldn't find it. However, I'm sure all of you have seen an IC. It is like a black box. So it is something like this. Okay? Is there anybody who hasn't seen an IC? Okay, good. So, whenever you have an IC like this, you just hold it in front of yourself and you see this little guy over here. Sometimes this is a half circle or sometimes this is a triangle. Depends on different IC. But whenever you see this guy over here, just hold it in front of yourself, hold the the op-amp in front of yourself so that this guy is up. Okay? So how do you number the terminals from the top left side? 1, 2, 3, 4, 5, 6, 7, 8. Is that clear? Whenever you see ICs and you want to understand about the number of terminals, this is the way. Again, one more time. From the top left, 1, 2, 3, 4, go right, 5, 6, 7, 8. This IC has 8 terminals. Sometimes you hear legs, 8 terminals, 8 bases, but here we use for the source terminals. Any questions? Here? Okay. This is an op-amp with 8 terminals, but we are going to use just 5 terminals. 3 other terminals are not usable for us for this class. You see here, offset null, and NC, which stands for no connection. Is that clear? I want you to learn op-amp here today for your life and never forget it. So this is nothing, an IC with 8 terminals. Now we know how to number the terminals, 1, 2, 3, 4, going to right side, 5, 6, 7, 8. So you see the terminal number 4 is V minus. What is that?
Negative part of the voltage terminal?
Yes. The power supply, the negative power supply, will be connected to this terminal. And what is V plus? Positive power supply. So whenever you have positive power supply, you have to connect it to which terminal? 7. Negative 1, 2, 4. So number 2 is called inverting input. Number 3 is non-inverting input. I'm going to talk about them more. And the number 6, terminal number 6 is output. So if I give you oscilloscope, which terminal would you connect it to? 6. Why? Because this is your output. Is that clear? Any questions about op-amp? Okay. We usually use this symbol to show op-amp. Okay. So we say positive is non-inverting input. So whenever you see positive sign, non-inverting input. And whenever you see minus sign, inverting input. Minus, it means I want to invert. That's why we use negative over here. So you see this guy over here, it means positive power supply, or this one, terminal number 7. And this one, negative power supply, means terminal number 4. And this one is the output, terminal number 6. So you see in different books something like this. This is an op-amp. Non-inverting input, inverting input, positive power supply, negative power supply, and this is the output. Is that clear for everybody? Questions? Easy? Okay. So if you want to see voltages and currents at each terminal, we use this figure. So you see IP. Why IP means positive? Means non-inverting. Okay? So that's why you say IP. IN, current, again, the direction of the reference current is inside, going inside the op-amp. That's why I have this arrow going inside. So this is IN. Why IN? Because this is negative, inverting terminal. And over here you see positive power supply, and this one is negative power supply. And what is this? This is the out. And do you see the current at the output? Again, going inside. This is our reference current, the direction of the reference current, going inside. And over here you see IC negative and IC positive. IO, I know, yes, it's that. It is just the reference. Questions? The terminal behavior of the op-amp is a linear circuit element. If you see this plot over here, op-amp has 3 regions. 1, 2, 3. But we are just looking for the linear region. We don't want to be in this region or this area. We call them saturation. If we are over here, we call it positive saturation. If we are here, we call it negative saturation. We just want to be in this area. Why? Why? What was that? Okay, here also transfer what? Voltage. So here it means it doesn't transfer voltage. It is? Yes, because we want to use the, yes.
The signal you're trying to amplify is clipped and it loses the data you're trying to transmit when it gets in saturated regions.
Yes. And one more thing, because we want the op-amp to be operational amplifier for us, to do some operations for us. If it is not in the linear region, it doesn't do anything for us. That's why we want it to be in this region. Otherwise, op-amp has no meaning for us. Just say V out is VCC. What is the use? I can directly get this voltage from the power supply. Or over here, V out is minus, this is minus VCC. So what is the use? Is that clear? So we want an op-amp to operate in this region. So over here you see, if A times Vp minus Vn, what is Vp minus Vn? The difference, yes, the input of the op-amp. And what is A? A is gain, is the scaling multiplier constant. So over here we have A, which is gain, multiplied by Vp minus Vn, or over here. If this one is smaller than minus VCC, it means smaller than our negative power supply, V out is minus VCC. Or if this term is greater than positive VCC, V out is plus VCC. But if this one is between minus VCC and plus VCC, we have V out equal to A times Vp minus Vn. What does this mean? For an op-amp, if we want to stay in the linear region, the output must be between minus VCC and plus VCC. Yes? Clear? So if you want to stay in the linear region of an op-amp, the output must be between negative VCC and positive VCC. It means if your power supply, the negative one is 10, and the positive one is also 10, so this guy should be between minus V10 and plus 10. It means the voltage at the output must be between minus 10 volt and plus 10 volts. Is that clear? Question? David, question? it says that for most op-amps, the recommended DC power supply voltages usually do not exceed 20 volts. And the value for A, or the gain, is not less than 10,000. Okay, usually. It's like this. So if we divide 20 over, if we say 20 over 10,000, we get 2 millivolt. What is now 2 millivolt over here? Why did I divide this one by A? What does it show? Huh? Okay, so which voltage? What is this one? What is this value? So what is it? Which parameter is it? This is VCC over A. Yes. What's your name? Anj? Anj. Okay. So VCC over A. VCC over A. So it means it is the magnitude of VP minus Vn. So 2 millivolts means the magnitude of Vp minus Vn. So it means the magnitude of Vp minus Vn. When we say Vp minus Vn, we say it should be the difference 2 millivolts. And we usually use very large voltage at nodes. For example, we use 2 volts. Is that clear? You have inputs, non-inverting terminal and inverting terminal. We usually don't put low voltage, or we don't apply low voltages at nodes. For example, if we apply 2 volts, how do you compare 2 volts with 2 millivolts? Convert 2 volt to millivolt. It means how much? Yes. It means 2,000 millivolts. Okay. So for example, if the inverting is 2,000 millivolts and non-inverting is 2,002, so the difference is 2 millivolts. But you see 2,000 millivolts and 2002 millivolts, we can say they are about the same. Is that clear? Yes? Okay. So that's why for an ideal op-amp, we say that Vp is equal to Vc. Or sometimes you see that it says that they are virtually grounded or virtual short. That is why. Is that clear? Questions? Yes. The voltage? Okay, I'm going to. Okay. I want to say that when we use an ideal op-amp, Vp is about equal to Vn. Why? Because we usually, when we use op-amps, DC power supply, the value for DC power supply usually do not exceed 20 volts. Okay? And value for A, the gain, is not usually less than 10,000. Okay? So if you say 20 over 10,000, it is how much? 2 millivolts. So what is this 2 millivolts? It is the magnitude of Vp minus Vn. So if I say over here, this VP is 2000. And this one is 2002. What is the difference? 2 millivolts. So, but we are talking about a large value compared to 2 millivolts. We are saying 2000 millivolts and 2002 millivolts. So that's why I can say these are about the same. That's why I use this term over here, virtual short, or sometimes you see virtual grounded. Clear? Thank you for asking this. Okay. But if you want to maintain the virtual short at the input of the op-amp, we have to have a negative feedback from the output. So that's why we use negative feedback, and we connect this output to inverting input, not to non-inverting. We connect it to inverting input. That's why we say that we have negative feedback at op-amp. To the negative, yes. And if you see the IC, it is designed so that the impedance at the input is so high. For example, here, it says it's very large, it's greater than 1 mega ohm. So when we have high impedance, it means what? If you increase the impedance, what would happen to the circuit? Current goes down. So when we say it is large value, it means the current is about 0. It's not equal 0 exactly, but it is about 0. It means when we analyze the circuit, we say IP is equal to IN is equal to 0. For which op-amp? For an ideal op-amp. Clear? So for an ideal op-amp, we have two constraints. One is voltage. We say that VP is equal to VN. And the other one is for current. IP is equal to IN is equal to 0. But again, I persist, about, this is about 0, but invokes different references, we see equal to 0. Clear? So for your future interview, when after 1 year you look for a job, if one person asks about op-amp, this is the basic, or this is the core content of an op-amp. Op-amp is nothing, this is just IC. If the interviewer put an IC in front of you, like 741, so it is an op-amp, and say how it works. It's okay, 1, 2, 3, 4, 5, 6, 7, 8 terminals we have. We just use 5 terminals. We usually use just 5 terminals out of 8 terminals, and it has 2 constraints. One is voltage constraint, another one is current constraint. What is the voltage constraint? We say VP is equal to Vn, and In is equal to Ip is equal to 0. And if he or she asks you, what's the meaning of virtual grounded or virtual short? You say the first constraint we have, the voltage constraint, which is Vp is equal to Vn. And if they say why Vp is equal to Vn, you can say that because usually power supply we are not going to go more than 20 volts, and the gain of op-amp usually doesn't go below 10,000. So 20 over 10,000 is 2 millivolts. So this is the difference magnitude or input voltage for the op-amp. It means Vp minus the magnitude of Vp minus Vn. But we are using large values at node voltages. Usually 2 volts. 2 volts, if you convert it to millivolts, is 2,000 millivolts. So if you say one terminal is 2000 and another one is 2002, we can say they are about same value. Clear? Questions? So, an ideal op-amp, Vp equal to Vn, Ip equal to In equal to 0. So, let's see what you have learned so far. For example, here, if positive power supply is 15 volts and the negative one is minus 10, so V out must be between minus 10 volts and 15 volts to be sure that we are in the linear region. Okay? So, the first example, we have this circuit over here. Question number 1. Okay. Calculate the output voltage if VA is 1 volt and VB is 0 volt. I give you 2 minutes. No answer? Okay. What's that? Negative 4. Figure out. Yes. What's your name? Oops. Okay, you set the negative 4. Yes? Okay, there is a circuit like this. We are looking for V out if VA is 1 volt and VB is 0. When you say VB is 0, it means it is grounded. There is no voltage over here. And VA is 1 volt. Is that clear? Okay. So we say VP, this is VP, and this is VN. One more time. This is VP and this is VN. So VP is equal to VB, which is 0. Yes? Okay. So for an ideal op-amp, we say VP equal to VN. So if VP is equal to 0, then VN is 0. Okay, this is one thing. The other one, we have constraint on current. So if you write node voltage for this node over here, how do you write? You have current, which is called I-25. How do you calculate this one? VA minus VN over 25 kilo ohms. So how much is I-25? Vn is 0. Va is 1 over 25, which is 1 over 25 milliamp. Is that clear? Is there any part which is difficult for you to follow? No? Okay. For the second one, we have another current which is I-100. So how do you calculate this one? Is V out minus Vn over 100 kilo ohms. So V out minus 0 over 100 kilo ohms, we have V out over 100 milliamps. Again, because over here we had kilo, here we have milli. So this is our circuit. For an ideal op-amp, we said IP is equal to IN equal to 0. So this is IN, this is IP equal to 0. So for this node, we have I-25 entering, I-100 entering, and IN, which is leaving. Okay, so minus IN is equal to 0. This one is 0. What is I-25? Is 1 over 25 milliamp. And what is I-100? Is V out over 100 milliamp. Equal to 0. So from here you can calculate V out, which is minus 4 volt. So you can still see over here, V out minus 4 is between minus 10 and 10. So we can say this op-amp is in its linear region. Clear? Questions? Yes. Okay, this part from this node to here, it's IN. We call it IN. Here, we call it IP. Actually, it has no meaning if you say this IN is exactly 0. Just to make it simple to analyze the circuit, we say it's 0. It's about 0. We have very, very, very small amount of current over there. Okay, one more time. You just write node voltage for this node. This one is I25 plus I100 minus IN is equal to 0. How do you calculate I25? VA minus VN. Because VB is 0, it means VP is 0. VP is 0 means VN is 0. That's why we have 1 over 25 plus V out over 100 equals 0. I explained from the class that all currents entering op-amp, all the currents entering. So V out, entering, entering, entering. This is the reference direction. The reference direction. Okay. B. I want you to solve this one. We repeat A for VA is 1 and VB is 2 volts. Any questions?
No, I think
Okay. Who got the answer? How much? 6. Yes. Now, VA is 1 volt and VB is 2 volts. So again, VP is equal to VB. This is VP. So what is VP over here? VB. And how much is VB? Is 2 volts. It means VN, it means this node is 2 volts. So how much is IB? Again, VA minus VN over 25 kilo ohm. Now here VN is 2. We have negative 1 over 25 milliamp. And for I100, again, V out minus Vn, which is now 2. So we get V out minus 2 over 100 milliamp. So we say again, I-25 is equal to minus I-100, the same equation over here. So if you solve this equation, we out will be 6 volts. Again, 6 volts is between minus 10 and plus 10, so it's this op amp is in its linear region of operation. Questions? Actually, op amps are very, very, very easy. Just two things. For the first one, we want the op amp to be in its linear region operation. And we assume that our op amp is ideal. If it is an ideal op amp, so we say Vp is equal to Vn and In is equal to Ip equal to 0. That's it. And for part C, if VA is 1.5, you need to find the range of VB that avoids amplifier saturation. Okay, for this part, again, we say that Vn is equal to Vp, and Vp over here is Vb. So now we are looking for a range for Vb so that our op amp will not go to the saturation region. So over here, again, the same thing. I-25 is equal to minus I-100, and I hope nobody has problem with this equation. And VA is 1.5. So what is I-25? 1.5 minus Vn over 25 milliamp is equal to minus V out minus Vn over 100 milliamp. Again, here Vn is equal to Vb. So just substitute it here. So 1.5 minus Vb over 25 is equal to this term. So from here, if you rearrange this equation, you get VB as a function of V out. So over here, I just divided by 25 to make it simpler. So we already know that if we want to stay in linear region, so V out must be between minus 10 and 10. Why minus 10 and 10? Because positive value for power supply and negative value for power supply. Plus 10, minus 10. So V out must be in between this region. So this range. So that's why we say V out must be between minus 10 and 10. If it was 12 and minus 10, you should say minus 10 and 12. So now for this circuit, yes.
Why did you put divided by V?
Just make it simpler.
Oh, okay.
You can use this one if you want. So V out is minus 10 and plus 10. So instead of writing V out, I say V out is 5 times VB minus 6. Must be between minus 10 and 10. So here I just add plus 6, all this equation. So I get minus 4, 5B, 16. And I just divide it by 5. I get the range for VB. If the value of VB is in this range, so we can make sure that if VA is 1.5 volts, so we are safe. Is that clear? Do you want me to repeat? No? Clear? Sure. Okay. Practice. Assessment problem 5.1. Do you have a question? No? I want you to enjoy the class. If you don't enjoy the class, just let me know straightforward. I can explain it, be happy. As long as I'm your teacher, I will explain everything for you, so don't worry. I will support you. Okay. We are going to study 4 kinds of operational amplifiers. They are very important. That's why I picked them up. But there are a lot. Usually these 4 are used for different purposes. That's why I'm going to explain these 4 amplifiers. So the first one is the inverting amplifier circuit. What does this mean? From the name, inverting. Okay? Yes, it inverts. Okay, this circuit is like this. When we talk about the inverting amplifier, you see this part is connected to power supply, but the positive is not connected to any power supply. So we can say this is kind of inverting amplifier circuit. So how do we understand? How do we prove it? Again, the same thing. Whenever you see op-amp, operational amplifiers, just follow the same procedure. Because we have to assume that our op-amp is an ideal op-amp. So if it is an ideal op-amp and we want it to be in linear region, and we assume that it is in linear region, and we have two constraints. So the first one for this one, again for this node, if you write node voltage for this node, you see IS plus IF is equal to IN. Is that clear? Yes. Is that clear? Yes. Okay? So the first thing, write node voltage for this node, this one. So IS plus IF is equal to IN. Why? Because IF and IS are entering and IF is leaving. The second one is Vn is equal to Vp. So over here, how much is Vp? 0. So it means Vn over here, 0. So Vn is 0. So what is Is? Vs minus Vn over Rs. So if Vn is 0, Is is Vs over Rs. That's it. And how about If? If is V out minus Vn over Rf. We call it Rf because it is feedback resistor. That's why we put Rs. So this If is equal to V out over Rf. So In is equal to Ipn is 0. So for this one, In, this equation, In is 0. So Is plus If is equal to 0. So we have Is from here, and we have If from here. So V out is equal to minus Rf over Rs times Vs. Because of this guy, we have over here this negative. That's why we call it inverting amplifier. Is that clear? Yes? So what is the scaling factor for this one now? Rf over Rs. So our scaling factor over here is this one over this one. Question? So for all amps which have equal power supply, it means V plus is equal to minus V negative is equal to VCC. So we can say this is the equation. Why? Because again we say V out is between minus VCC and plus VCC. Is that clear? So what is V out? V out is Rf over Rs times Vs. So this term is between minus VCC and plus VCC. Sometimes we write it like this. This one means when I say the magnitude of this one is smaller and equal to VCC, it means this. So what does an inverting amplifier do? It inverts the output. and change the scaling. How? RF and RS. So it is RF over RS. So those two resistors are important when we use inverting amplifier. So the next amplifier is the summing amplifier circuit. So what is the summing amplifier circuit? The output is?
It takes two values.
Yes. Is the sum of input voltage. Yes. How do? Negative sign, invert. That's why we call it inverting, because we have negative sign. Which question? Okay, we assume that our op-amp is an ideal op-amp, and it is in linear region. So we said that when our op-amp is an ideal op-amp, so we have two constraints. The first constraint is voltage constraint, which is Vp is equal to Vn equal to 0. And the second constraint is equal to Vp. But here, because Vp is 0, that's why we say Vn is 0. Over there, you see V, okay, it's not clear. Okay, this one is Vp, you see? So this is grounded. It means 0. So because Vp is 0, it means Vn is 0. Okay, for the next amplifier, the summing amplifier circuit is something like this. Again, you see negative side over here. We have different voltages as input. VA, VB, and VC. And this one is grounded. Again, we have the feedback resistor over here, which is from output to the inverting input. Just to make sure that we are not going to go inside the saturation region. That's why we have this feedback. But if we have this feedback, it doesn't mean that we are in linear region. Okay? Okay, again for this one, write the node voltage for this node. Vn minus Va over Ra plus the second branch, Vn minus Vb over Rb, and the third one, Vn minus Vc over Rc plus Vn minus V out over Rf plus In, it means minus, is equal to 0. How much is the value for In? 0. So here we don't have this term anymore. And what is Vn? How much is Vn? 0. Why Vn is 0? Because Vn is equal to Vp. How much is Vp? 0. That's why Vn is 0. So we have 0 all over here. So we get something like this. If you rearrange the circuit, you will get this equation. Question? So just rearrange the last equation, we get something like this one. So as you can see over here, the output is the summation of input voltages. So you can go more than 3 voltages. For here, just for example, we put 3 voltages. So if we have 3 voltages, the output is equal to VA multiplied by something plus VB multiplied by something plus VC multiplied by something. So now if we assume that RA, RB, RC, and RS all are equal, we'll get something like this. And if we say again RF is equal to RS, we have something like this. It means output will be the summation of input voltages. Questions? Yes.
So does RF always have to go RS for it to actually be the same?
It should not be always like that, but we say we assume if they are equal, you get something. Even you don't get equal, again, it is the summation, but you have to multiply by a scaling factor, which all depend on the values of RF and all input resistors. Questions? So this is summing amplifier. Very easy. That is the summation of input voltage. How do we get this equation? Again, for using those two constraints. Practice. Assessment problem 5.3. The part of op-amp is already posted on Brightspace. Is there anybody who cannot access the notes, which I already posted? No? Okay. The next one is the non-inverting amplifier. So non-inverting amplifier, you see inverting input is connected to a power supply, but inverting input of the op-amp is connected to a resistor and then ground, but non-inverting is connected to a power supply. So whenever you see something like this, it's kind of non-inverting amplifier. Yes?
Who's the
Again, the part of short, the virtual short, what IN is equal to IP, equal to 0. Okay, I explained that usually when we use operational amplifier, we have power supply, positive and negative, right? So this value usually doesn't exceed 20 volts. In practical, you have power supplies. When you use this IC, you should not go more than 20 volts, okay? So, and for the gain of amplifiers, usually you should not go less than 10,000. Okay, if you divide 20 by 10,000, how much you would get? 2 millivolts. Okay? 2 millivolts. What is 2 millivolts? Is the magnitude of Vp minus Vn. Yes? Is that clear or? Because you say Vc divided by A. Vc divided by A means the magnitude of Vp minus Vn. So the difference is 2 mV, 2 millivolts. But in practical, when we use op-amp, we use, for example, 2 volt, 3 volt as an input voltage. Okay, if you convert 2 volt to millivolt, 2 volt is 2,000 millivolt. Clear? Okay. So for non-inverting amplifier, again, we do the same thing. IP, IN equal to 0. So what is Vp over here? This is Vp. Is equal to Vg, V generator. So this node is Vn. So how much is Vn? Vg. Again, if you use voltage divider, you will get something like this. But again, I explained over here for the students who don't know voltage divider or the students who don't like to use voltage divider. Again, for this node, Vn minus 0 over Rs plus Vn minus Vout over Rf plus In, which is, or minus In, which is 0, is equal to 0. Okay, clear? Okay, so from here, we have Vn over Rs plus Vn over Rf is equal to Vn over Rf. You just rearrange this equation. You will get this one. V out is something times Vg. So for this amplifier, we don't have negative sign. Because we don't have negative sign, we say this is non-inverting amplifier. So V out is scaling factor times Vg. What is our scaling factor over here? Rs plus Rf over Rs. Clear? Okay. So again, the same thing. If you want our op-amp to operate in a linear region, so V out must be between minus VCC and plus VCC. So what is V out? Is this one. If you put this one over here, we get this equation. Practice assessment problem 5.4. And the last op-amp is the difference amplifier circuit. So we have learned inverting, summing, and non-inverting. And the last one is the difference. Okay, the difference is something like this. You see voltages at both inverting and non-inverting inputs. Again, write node voltage for this node, which is Vn minus Va over Ra plus Vn minus Vout over Rb plus In is equal to 0. When I put plus means minus, I just wanted to say it's algebraic summation. Okay, and we know that this guy over here is 0, and Vn is equal to Vp. And from this one, this is 0, so we have this equation. From here, we go to this one. And again here, use voltage divider to find Vp. Again, for students, don't like to use voltage divider or don't know how to use voltage divider, I put these equations over here. So here is Vp. Write node voltage for this node. So this is Vp minus 0 over Rd. I didn't put minus 0. And Vp minus Vb over Rc. Again, we have Ip, which is 0, plus Ip, or minus Ip is equal to 0. So we get this one. Just rearrange this one. You have Vp as a function of Vb, which is this. Is that clear? have two equations. The first equation was this one, and the second equation was Vp as a function of Vp. Just you say that Vn is Vp, so substitute Vp into this equation, you will get this one. And over here, I want to get rid of Rb, that's why I multiply by Rb. So I just rearrange it then, because I just wanted to have V out over here. You get something like this. Again, rearrange this equation, you get this one. Some scaling factor times Vb minus some scaling factor times Va. That's why we call it the difference amplifier. Again, if you want this term to be equal to this term, okay? So, Ra over Rb must be equal to Rc over Rd. Make sense? Is that clear? If we want, it is the last equation, but in case we want to make it simpler, and we say this term, we want it to be equal to this term, this is another condition. So, for this one, Ra over Rb must be equal to Rc over Rd. So that's why we get for V out this equation. If R A over Rd is equal to Rc over Rd, this equation will be this one. This one. So for practice, assessment problem 5.5.